Hello, everybody. So I think we'll start with this afternoon's session. First talk will be given by Vincent Martinez from City University of New York, and the title is Reconstructing External Force by a Low Mode Observation into the Navier-Stokes equations. Vincent.
Check. Thank you very much, Vincent. Also, thank you very much to the organizers for having me here. It's my first time being part of an I&I program, and really looking forward to being here for the rest of the month. As Vincent said, I want to talk about reconstructing external forces in the Navier-Stokes equations. This is, in some sense, this is essentially an inverse problem in the same spirit that Marcel was talking about a few days ago. The setup is the following: we observe an incompressible fluid, and it's being perturbed externally. You're only able to observe finitely many length scales of this level. The way that we're going to model those observations is by assuming that we observe finitely many Fourier modes, and that those Fourier and that the full series to which which corresponds to those Fourier modes satisfy the Navier-Stokes equations, which are being forced. And so the main question is, well, let me write out this model first. So the whole for the rest of the talk, I'll be talking about. I'll be restricting myself to the two-dimensional case and with periodic boundary conditions. And the point is that the force is unknown, but we observe a projection of the solution for all time. So we model the observations as this continuous time series of the low modes. And so the question is, can we reconstruct that? And of course, to identify conditions on the observations that would ensure that. Okay, so what I want to emphasize here is that this setup is incredibly ideal. There was a talk the other day where there was a sort of model of a space where, if you have more information about the model, right, it increases as you go up. You have more information about observations. Well, in this setup, we are all the way out at infinity. We have a perfect model and perfect observation. So incredibly ideal, but it's a place, it's a starting point to understand, right, what are the difficulties beyond underneath this problem. Okay. Let me also mention that I am aware that it's an ideal setting, but I hope to interest that some of you will be interested enough in this talk, and that we could form a bridge to something more practical, realistic. All right. So this is the basic question: can we reconstruct that? So I don't have much time to get into all the details. I hope to just bring you to the point and describe what the algorithm is to do so, and how, and basically show how the low mode observations get leveraged to do that. At the end of the day, well, what's going to happen is we're only going to be able to reconstruct the force on the up to the length scale that we observe, and anything beyond that would be unknown. Okay. So let me just describe what some of the difficulties might be. So if you have low mode observations, there's a very naive thing you can do to come up with a guess for what F is, okay? In some sense, every vector field is a solution to the 2D Navier-Stokes equations for some forcing, right? Because what you do is you take the vector field, you plug it into the equations, and it just gives you a right-hand side, right? And so one naive guess for an approximate, naive guess or naive approximation to the force would be to just plug in your observations. And by the way, I like using this functional notation where you project the equations onto divergence through vector fields, and you view the equations as an ODE in an infinite dimensional space. So I hope you won't mind. So A is going to denote the negative Laplace operator, and B of UU is simply going to be this nonlinearity but projected onto divergence through vector fields. And we have PF. So if we assume that F is divergence free at the onset, we can just say this is F. Okay, sorry. So here's the functional formulation of Navier-Stokes. So let's just plug in the observations directly into the equation. And I'll just use a shorthand here. Oops. And I'll define this to be our initial guess for the force. Okay. Now, obviously, this isn't the force, right? Because the low modes are not an exact solution of the Navier-Stokes equations.
Excuse me, Vincent. The end is what?
Oh, thank you. Yeah. So Pn denotes.
Not BBN, but
I know. Yeah, thank you.
But the input of Bn is the original U?
I'm so sorry. Yeah, thank you. Thank you. Yeah, thank you. I'm sorry. So you see, this is concentrated on low modes, right? Yeah. Thank you. I'm very sorry.
So you found the solution of Galette?
Yeah, this is good. This is just a naive guess, right? I'm just going to use this to motivate the ideas. So, of course, if you just take the Navier-Stokes equations and project them, which is what I just wrote, yeah. Right. Then you have you've committed some errors, right? There are some errors left over because you don't have any information about the high modes. And so when you subtract these two things, right, you're left with this expression. And of course, you'll recognize this is essentially this is the Reynolds stress of the equation when you filter with when you use when your filter is just the Fourier projection. And so reconstruction of the forcing, even at the low modes, really it's necessary for you to overcome, the Reynolds stress. And what this amounts to is being able to somehow find a way to reconstruct the unobserved scales, or in this case, the high Fourier modes, but only in such a way that you can only use the low mode observations to do so. Right. So we need to. This is an error. I'll refer to this as the model error, because we don't know what the force is, and we've guessed what it is. Right? It's F0. Our guess for it is F0, and we want to decrease this. Okay, so it seems at a first glance it seems so you have to solve the closure problem to solve this problem. It turns out that you don't, okay? Because if you if you only ask for reconstruction asymptotically, because we're making observations continuously in time, then it turns out it is possible to reconstruct F on the low modes. The hope for doing that comes from a classical theorem of Ciprian Voish and Giuseppe Poli. From 1967. It's kind of remarkable that this was proved so long ago. Let me write the theorem. So if you're given a force and a viscosity, then one can identify a sufficiently large projection so that the Navier-Stokes satisfies the following property, such that if you had two solutions of the Navier-Stokes equations, so this is one initial data and another initial data. You look at the difference between two solutions corresponding to the two initial conditions. If you knew that asymptotically they were converging to each other, then in fact, the two solutions coincide at time infinity. And so basically the Navier-Stokes equation has a form of asymptotic enslavement of scales, where if you knew that the low modes were converging to each other sufficiently many of one force, then in fact the whole solutions are converging to each other. And this is essentially the phenomenon that one wants to exploit, or the mechanism rather one wants to exploit in order to do this, because the only question now is, how do you actually reconstruct those high modes? And so we need to propose some systematic way of doing that.
May I ask a question?
Yes, please.
I don't remember the critical end, how many modes they have, it depends on the viscosity and the Poisson curve.
It does. Yeah.
So how do you use it when you want to how many capital N if you do not know the force?
This is true. This is a practical issue, right? You don't know beforehand how many you need to use unless you have more information about the situation itself. So, for instance, in the context of a turbulent flow, we know that there are only finite many degrees of freedom, but it's very large. Maybe depending on your situation, you have an estimate for for instance, the Reynolds number, right? In that scenario. And this n is going to be proportional to the Reynolds number. Okay. The precise estimates for lower bounds on upper bounds on how big n needs to be were obtained by Idris TT, Don Jones, Idris TT, and others. Of course, there's an estimate in Foresh Purdy as well of how many we need. Okay. So we need a way to systematically reconstruct high modes, and two, reconstruct F simultaneously. Okay, and so the way that we're going to solve the first problem is going to be an idea from Azumani Olsen and Titi from 2014. Is there a third one? No, okay. So dealing with issue one is a result of Azumani, also in Titi in 2014, where they proposed the following algorithm for the data assimilation. So they consider the following system. Okay. And they're able to show that you can choose your mu sufficiently large and your n sufficiently large, again, depending on the viscosity and the forcing. So here, nu and f are given again. So that you can guarantee that this solution converges to you asymptotically. Okay. So basically, the way that they leverage observations is by directly inserting them into the equation, the original system itself. And the idea behind adding it here, I mean, okay, in the context of data simulation, this is referred to as a nudging scheme. But the novelty in Aswani-Wilson and TP is that, okay, one, they don't use just Fourier modes, but you can consider other observables here. Is that they basically define the nudging scheme for PDEs, okay? And what that amounts to is finding a good way to interpolate your observations into the phase space of your system. All right. So in this case, the phase space is, trigonometric, infinite Fourier series, which are square integral and divergence rate, etc. And Pn is sort of clearly in the phase space. All right. So you see so the observations are being inserted directly in this way. And if you see, if you imagine these to just be scalars, for example, then what's the effect of this term, right? When V is larger than U, then let's say that this term is positive, okay? Just hop on the Ferris wheel with me for a little bit. And this minus sign forces the V to decrease towards U. And if V is beneath U, then it will force it to go towards U. So this is always driving the system towards the observations, but only on these scales, or only on the scales that you observe. And then through the Fourier-Prodi mechanism of determining modes, that's what that property is referred to, the large scale, the small scales will also contract. Right? So this is a feature of the deterministic system that's being leveraged here. Okay, so secretly, there are high modes in V, right? Or implicitly, I should say. And so those are the ones we'll take to reconstruct the high modes. Okay, but of course, we have to slightly adapt this because we don't know what F is. And so what we'll do is we'll come up with a way to produce, systematically produce new guesses for F, or approximations to the force that self-improve as you collect observations. And so let me write the algorithm here. So let's start off with an initial guess. It could be the very first one I wrote down earlier, where you just here it is. You just plug the low modes into the nonlinearity and then project the nonlinearity back onto the low mode subspace. So let this denote your initial guess. And then with this initial guess, we're going to generate a guess for the high modes via this nudging scheme. Okay. And once this has been integrated forward, we now have a solution to this equation with the wrong force, right? And then we define, we reconstruct the full velocity field by taking our observations and adding the complementary projection of the equation generated by Mendel as packed for the. Oh, thank you. Here's the reconstruction of the velocity field. From this, we'll now generate a new F by taking this velocity field and plugging it back into the equations. and that will be our update for the forcing. Okay, and so the algorithm is to iterate on this procedure. The idea, as you can see, basically the idea is to use the equations as a way to filter out errors. Of course, I haven't showed why those errors are actually getting filtered and are decreasing. Okay, so let me, for the last half of the talk, I'll go through that. Okay, so this essentially gives the first approximation, the first non-trivial approximation to the force. And so now we continue. And suppose that you've obtained a force at stage J, okay? And as you can see, the force depends on our previous reconstruction of the velocity field, so it depends on uj. Sorry, uj minus 1. Where uj minus 1 was itself constructed by taking the low modes, so the data, and then the high modes of the nudging scheme, which was defined from the previous forcing. Okay. Okay. And so I'll just write it down. You generate everything again. You look at you generate a solution to the nudging equation. You take, we define uj to be your low mode observations plus the high modes of the newly generated high modes, and then you define your new forcing. Okay, so now let's look at the error committed by this algorithm. Okay. So this is just fj plus 1 minus the true forcing, and now we subtract these equations. Right? We have dt uj plus uj and subtract off force from the true velocity field. So remember that uj was the true low modes. Right? So this being the linear part of the equation, the low mode contributions will cancel identically, right? And so you'll be left with just the linear part of the equation applied to the high modes. Okay? And then of course you have the subtraction of these two nonlinear terms. So, like I said, we'll be left with the complementary projection of the linear part. And then here, we have the differences between the nonlinear terms. And if we unpack this, right, this was I'll just use a shorthand here. I hope you don't mind. This is UJN plus VJ and high modes. And so it'll cancel the low mode contributions here, and then you'll get a mixture of terms. Right? So this will simplify. So the low interaction cancels out, and you're left with. So dBm will just be the derivative of this of B, but along this function. And notice here, this is going to be the difference between Vj but only on the high modes. Plus, sorry. Qn, oh, sorry, Q is I minus, sorry, Pn. The difference, sorry. These are W's, and W will be Vj minus C. Okay. And so now if we project the error onto low modes, you see this drops, right? Because this is localized onto low modes. And now you have low mode projections of this term and this term. Notice that they're entirely in terms of the original solution. I'm sorry, I believe this is Q. So high modes here. The full solution. And just the projection of the high mode interaction between the differences. So this difference, one can think of this as the synchronization error. Because in light of the Aswani was also TT result, we know that that would go to zero if you had perfect information of the force. So you have now the model error is entirely represented in terms of the synchronization error, but the synchronization error was defined from the previous force. And so one just needs now to estimate, obtain a good estimate on the synchronization error, and you get an estimate of the current model, the model error at stage j+1 in terms of the model error at stage j, the previous stage. The catch, so at the end of all this, what you get is that the low mode projection of j+1 is less than or equal to some constant times the model error from the previous stage. And now in order to get this to converge, we'd like the C to be a small constant. Okay? When one estimates the synchronization error, so I should write it like this in fact. So it will be of order of the synchronization error. One can in fact obtain estimates for this that are 1 over square root of mu, which was a tuning parameter in the algorithm, times a constant. And so now one sees that one just needs to choose mu appropriately large for this algorithm to converge. And so I know I've skipped a lot of details, but this is the idea behind this scheme. And at the end of the day, what you recover are the low modes of the force. Okay. You can also, how much time do I have? Oh, there's no time. So I will stop now.
We're waiting for the computer to set up the next part. We have questions, time for questions. Go to a bit, please.
In practice, in realistic application with nudging, that one of the issues, of course, that the data are not the same temporal resolution.
I'm sorry about the word.
In a lot of practical application of nudging, one of the issues that the data don't have the same temporal resolution as you would like to have in a numerical model.
I see.
How this will cope with that?